what I'm controlling. It's a mode inside.
Okay, everybody, it is section 4.4 on applied maximum and minimum problems. This is so stinking hard. Some of the questions in this chapter are really difficult. I don't know, put stars everywhere on your page to show yourself how hard some of this is. I'm sorry, but it always shows up. It's a big part of calculus. I mean, basically it's calculus in action. It's word problems with calculus. Oftentimes you won't refer to this topic as applied maximum minimum problems. It'll be referred to as optimization. So when you optimize something, what are you doing? You're making it as good as possible, right? So in terms of calculus, optimization refers to problems in which one quantity must be maximized or minimized. And it's commonly, things that are commonly maximized are things like area or volume or profit. Things that are commonly minimized are things like distance, time, and cost. So again, this is a very real world sort of thing. If you had some business and you want to maximize your profit, maybe calculus can help you figure out that optimal setup for your business. Or if you're traveling between some distances, maybe calculus can help you figure out the minimum distance you need to travel. So there's quite a few steps here. You got a lot of writing to do. As if this section wasn't tough enough, you got to start by getting a cramp in your wrist. I've got 6 steps for you. I'll fly through them here. Number 1 is always when you do word problems, try to draw and label a picture. Number 2, find the objective function. In other words, write a formula for what you want to optimize in terms of the other variables in your picture. So there should be one thing you're trying to optimize, whether it's area, volume, profit, distance, time. So you want to write a formula for that in terms of the other variables. 3, reduce the objective function to one variable. So if you start off by having a whole bunch of variables, you got to get it down to one by finding other relationships between the other variables. 4, identify the domain of the objective function. 5, differentiate. So all of that, once you got all those first 4 steps done, you can finally take the derivative, and then you're going to find and test the critical numbers and maybe the endpoints of the domain. Alright, find 2 positive numbers whose product is 10,000 and whose sum is a minimum. So let's start by designating for the 2 numbers. We've got our first number and we've got our second number. Why don't we call the first one x and the second one y. Now what we're trying to optimize, in this case minimize, is the sum. So we want to come up with, I guess the first question is draw and label a picture, but there's not much picture we can draw. There's no picture we can draw when we're just talking about numbers. So we're going to do go to number 2. Find the objective function. Write a formula for what you want to optimize, well that's the sum, in terms of the other variables. So we want to write a formula, s equals, and we want to write it in terms of x and y. But here's the thing, if we just put x plus y here, we have 2 variables. And the third step says, get it down to just one variable. You don't want to have 2 variables, you just want one. So we have to figure out a relationship between x and y so we can get rid of one of those variables. Well, it tells us right here that the product of the 2 numbers is 10,000. So we know that x times y equals 10,000. And then we could solve for either one of those variables. It really doesn't make a difference at all. I'm going to solve for y. I don't know why, ha ha ha. So in order to do that, we have to divide both sides by x. So this is what we get. So now we can do this step 3 where it says to express the objective function in terms of one letter. We can do that. We have x plus, I'm not going to write y, I'm going to write 10,000 over x. And eventually we're going to take the derivative of this, so it might be easier to write this as x plus 10,000 x to the negative 1. This will make it a little bit easier for us. Okay, step number 4 before we take the derivative is to find the domain of the objective function. So what's the domain of the sum? Is there any restrictions on the sort of numbers? Yeah, actually there is. It says right here that it's 2 positive numbers. So our domain is that x has to be greater than 0. Can it be equal to 0? No, 0 is not positive. So this is our domain right here. X is greater than 0. Notice we don't have to talk about y here because once we got down to this point here, we only have x in our objective function. So in this objective function, the domain of x has to be greater than 0, has to be positive. This is our objective function right here, written in terms of one letter. So we're all set up to do step 5, take the derivative. So that's what we'll do now. We have to find, if this is what s equals, the function equals, we have to find out what s prime equals, the derivative. Well, the derivative of x is 1, and the derivative of 10,000 x to the negative 1. Well, the negative 1 comes down, so you have negative 1, I'm not going to rewrite that negative 1, times 10,000, so negative 1 times 10,000 is 10,000, and then x to the negative 1 is going to become x to the negative 2. And why don't we rewrite that as 1 minus 10,000 over, this is a flipping negative, x squared. And now we're going to do what we did last day. And remember what we did last day, we said when we found these derivatives, we like to have them with a common denominator. So this is 1 over 1. Our common denominator is x squared. So we will have to multiply top and bottom by x squared. We get x squared minus 10,000 all over x squared, and you can factor the top there. So I have x minus 100 and x plus 100. We have a difference of squares there, all over x squared. Great, we have differentiated the objective function. Now we need to find and test the critical numbers. So this is just like what we did last day. I'll write over here critical numbers. To find the critical numbers, you need to see where the derivative does not exist. When does it not exist? It doesn't exist when x squared equals 0. So I'll put does not exist when x squared equals 0, which means when x equals 0. So that's one of our critical values or critical numbers. The other thing we have to do is see when does this derivative equal 0. Well, it's going to equal 0 when the numerator equals 0. In other words, when x minus 100 times x plus 100, when does that equal 0? Well, that's easy. That's when x equals 100 or x equals negative 100. So there's our three critical values or critical numbers. So we're going to put those on the wiggle graph. But remember, we already set up here in the domain, x has to be greater than 0. So on the wiggle graph, I'll put them all on for right now, negative 100, 0, and 100. But this part of the graph, we're actually not even worried about. Okay, it's only these two regions, these two intervals that we have to concern ourselves with. Now, what are we going to do? We're going to test those two intervals. Where are we going to plug our test number into? We're going to plug it into here. Okay, notice the bottom is squared. That's great. When you have something squared, or to the 4th power, or 6, or any even exponent, why is that a good thing? Because whether you put a positive or a negative number there, it's always going to be positive. So we know for all our tests, the denominator is going to be positive. All we have to look at is the numerator here. So let's pick a number between 0 and 100. How about 3? 3 minus 100, that's negative. 3 plus 100, that's positive. Negative times positive is negative. Remember the bottom was positive, so negative divided by positive is negative. So this is negative, which means our function would be decreasing here. Pick a number bigger than 100. I'll pick 200. 200 minus 100 is 100. That's positive. 200 plus 100, that's also positive. And this was positive. Positive, 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 it's all positive. So this side, this interval is going to be positive, which means it's increasing. So we have decreasing and then increasing. What does that mean we have here? That means we have a minimum. I sure hope that's what we were looking for here. It was. We wanted the sum to be a minimum. So we have found that the sum will be a minimum when x is equal to 100. But do we need to know what the minimum is? You actually don't. So you have the answer. The answer is, I'll just put this down here, the two numbers are 100 and, how do we get the second number? Well, this is what x is equal to. So we go up here and we see that the way you get y is you go 10,000 minus 100, and if you go 10,000 minus 100, you're going to get another 100. So the two numbers are 100 and 100. Say they wanted you to actually find out the minimum sum. What would you do then? Well, then you would take this 100 and you would plug it back into the original function, which is right here. Or if you just think about it, since you know the two numbers and you want to find the sum of them, you just add them together and you get 200. Okay, pretty tough, eh? Here comes another one, even harder. Find the points on the parabola y equals 6 minus x squared that are closest to the point 0, 3. Definitely want to draw a little picture here to help you get an idea of what we're doing here. So the parabola y equals 6 minus x squared, well, it's parabola because it's x squared. If you were to write this in the normal descending way, it would be like this, and you can see that it faces down because it's negative, and its vertex, this is actually in vertex form, the vertex is at 0, 6. So we're at 0, 6, it faces down, and it would be the regular shape, over 1, down 1, over 1, down 3, etc., etc. But I don't think we need to be that detailed about it. Let's just draw a parabola like this, and then the closest point is 0, 3. Well, this was 0, 6. We want to go halfway about there, and we want to know which points on the parabola are closest to that point there. Now, just to get an idea of what that would look like, the closest points, there'd be one on this half of the parabola, one on this half of the parabola. So I'm just going to draw one here and one here. This point up here, remember, is 0, 6. This point here is 0, 3. And we're interested in this distance from the blue dot to the purple dot. Or the same distance there, but I'm going to draw it. There's symmetry with the parabola, right? So it's going to be the same distance on the other side. Now, I don't know what that point is, so what I'm going to call that point is x, y. And what's going to help us here is the realization, this is the hard part of the question, if you don't figure this out, you can't really solve it, is we're interested in that red distance right there, and we can look at that like we're going to go here and here. We're going to make a little right angle triangle there. I know that's very small, hard to see, but we're interested in the hypotenuse of that red right triangle there. So with that red right triangle, I'm just going to draw it down here. The same thing. What is this distance down here? What's the distance of that? Well, it goes from the point 0 as its x up to x. So this distance here is x. What's this distance here? Well, it goes from 3 up to y. So the distance from 3 to y is the same as y minus 3. And we want to know this distance right here. I'll call it d. Okay, so the equation we can now use is the Pythagorean theorem. We can say that d squared equals x squared plus y minus 3 squared. But we have two variables here. Remember, we only wanted to have one variable. How can we change that? Well, we have a choice. We can either plug this y amount right here, this 6 minus x squared, into that y, or you could solve for the x squared and plug that in here. Maybe I'll try that. Let's solve for the x squared. If we move the x squared over here, we'd have x squared, the 6 would be here, and the y would come over. So we'd have 6 minus y. So now, instead of writing x squared here, I can write 6 minus y. That's what x squared is equal to. So I have 6 minus y plus y minus 3 squared. So let's expand the binomial. We have d squared equals 6 minus y plus y squared minus 6y, right? This is y minus 3 times another y minus 3. And if you do all the multiplying, you're going to get minus 6y plus 9. I think we can combine some of those terms. What do we got? We got a y squared. We have negative 7y. And we have plus 15. Now, you might be thinking what you want to do here is take the square root of both sides. Don't do this. You might be thinking you're going to have d equals the square root of y squared minus 7y plus 15, and then take the derivative of this, and it's kind of ugly. In fact, you don't even know how to do this yet. We'll learn later. But that's a very ugly derivative because you have it all in square root. So here's a little fact that's very useful with these distance questions. If you're trying to minimize, that's what we're trying to do, trying to get closest to the point. So we're trying to minimize a distance squared. It's exactly the same as minimizing just the distance itself. So what I'm saying is, I'll write it here, minimizing d squared will also minimize d. They're equivalent to each other. So I can just, I know this is a strange step, but I can just kind of drop the squared here because by minimizing d squared, it means you also have to minimize d. So we have d equals y squared minus 7y plus 15. And we've done it. We have our objective function. We only have one variable that we're working with here, so we're ready to take the derivative. Okay, the derivative is d prime, and it's actually a pretty easy derivative. Take the 2 down, minus 7. And then what we want to do is find the critical values, critical numbers, critical number. And in order to do that, we want to know, when does this not exist? Well, it always exists. Or when is it that it equals 0? So I would have 2y minus 7 equals 0. That's pretty easy to solve. 2y equals 7. Y equals 7 over 2, which is the same as 3.5. So we have a critical number, and we can put it on our wiggle graph. Where am I going to do this? I'll put it over here, 3.5. And if we put a point down here, remember, we're going to test it right in here. If we put a point down here like 0, you get 0, take away 7 is negative, which means this is decreasing here. And if you put a point bigger than 3.5, like 5, let's say, 2 times 5 is 10, minus 7 is 3, that's positive, so it is increasing. Decrease and then increasing, that means we have a minimum. That's exactly what we wanted to find. So we've done it, we found our minimum. Our minimum takes place whenever our y value is 3.5. Notice we should get 2 of them. We should have one here with a y value of 3.5 and one here with a y value of 3.5. How do we get the x values? We're going to plug it into this boxed one right up here. So we're going to have 3.5 equals 6, what is it, 6 minus x squared? 6 minus x squared. Bring the x squared over. Bring the 3.5 over. You get x squared equals 2.5, or x equals the square root of 2.5. Don't forget, you have to put plus or minus because you're taking the square root, solving by taking square roots. You have to put plus minus. So we have our two answers. One answer is positive root 2.5 with a y value of 3.5. And the other value, the other point, is negative root 2.5, comma 3.5. Those are the 2 points here and here that are closest to that point there. 2 points on that parabola, I should say. Okay, one more for today, then more next day. Tough, so hard. A cereal box in the shape of a rectangular prism is required to have a capacity of 5,000 centimeters cubed, and the thickness of the box must be 10 centimeters to allow for a comfortable grasp by most people. What dimensions of the box require the minimum amount of materials? Everything's minimum today. So we're talking about a rectangular prism. Looks something like this. And it tells us flat out that it must be 10 centimeters thick. So that would be this dimension right here, right? And it talks about capacity. Capacity is the same as volume. So in order to get volume of this thing, we need to know the length of this. So I'll put L, we don't know the length, and we need to know the width. Sorry, the height. We know the width. The width is 10. So these are our two dimensions. And of course, when we're talking about volume, it equals length times width times height, which means we have, well, the width is 10, so we have 10 times length times height. And we know the volume. The volume is 5,000. So if 5,000 equals 10 times length times height, divide by 10, you get 500 equals length times height. Now, we want to use the minimum amount of materials. When you're talking about the materials of something like this, what are you talking about? You're not talking about volume, you're talking about surface area. So what we need is a formula for surface area. And the formula for surface area is, you got to get the area of this face right here. You do that by going length times height, and there's 2 of them. So you'd have 2 length times height. Plus, you need to get the area of this face here, which is 10 times h, and you have 2 of those. So it'd be 2 times 10 times h. And then you get to get, we did this one already, then you have to get this one, which is length times 10, or 10L. And there's 2 of those. So 2 times 10 times L. So if we simplify that, you have 2LH plus 20H plus 20L. But again, we have this problem where we have 2 unknowns here, L and H. But it's easy to simplify that, or to fix that problem. We're just going to isolate one of these ones. Why don't we get the L by itself? So we have L equals 500 divided by H. So that's what we're going to plug into all the L's here. So we're going to have 2 and then 500 over H times H plus 20H, nothing to do there, plus 20 500 over h. These can cancel, so you end up with, I guess I'll keep the surface area, 2 times 500 is 1,000 plus 20h. 20 times 500, what's that, like 10,000 over h, but why don't we write it, since we're going to take the derivative of this eventually, why don't we write it as h to the negative 1. So now we have what we want. We have the objective function, only one variable, and what do we know about domain? With the domain, your length and your height both have to be positive, right? We're talking about distances, lengths, so h and L both have to be more than 0. Alright, we're ready to take the derivative. So that would be SA prime equals, well, the derivative of 1,000 is just 0, so there's nothing to do there. Derivative of 20h is 20, and the derivative here, the negative one comes down, so you have minus 10,000 h to the negative 2, which means it's a flippant negative h squared. And as we've said several times, what we want to do is we want to get it over a common denominator. So multiply top and bottom here by h squared. You'll get 20h squared minus 10,000 all over h squared. And let's factor the top by taking out a 20. You'll have h squared minus 500 all over h squared. Great, now we can get the critical values. Critical numbers. Okay, when does the derivative not exist? It doesn't exist when the denominator, h squared, when it equals 0. When's that? When h equals 0. So there's one critical value. The other thing we have to know is when does the derivative equal 0? And that would be when the numerator equals 0. In other words, when does 20 times h squared minus 500, when does that equal 0? Well, you can ignore the 20 because you can divide both sides by 20. So you're left with this. I'm going to solve it this way. Move the 500 over, take the square root of both sides. You get h equals plus or minus the square root of 500, which, if you want to put in simplest radical form, which is a good idea, 500 is the same as 100 times 5. Square root of 100 is 10, so you have plus or minus 10 root 5. Do the tree if you don't know what I'm talking about, right? 500, 5 and 100, 10 and 10, oh, there's a pair, 10 root 5. Okay, so those are the numbers we need to put on our wiggle graph, except our domain has to be positive. So you don't have to worry about all these. You only have to worry about these two sections right here. Where are we going to test those ones out? We're going to test them out right here. Denominator is h squared, so you don't have to worry about the denominator because it's just going to be positive. You don't have to worry about the 20, that's always going to be positive. So you actually only have to worry about this, the h squared minus 500. It probably would have been actually easier if I just left this as root 500. Maybe I'll do that. So this is root 500 here, this is 0. Root 500, I don't know. I know something between 0 and root 500. I know 1 is less than root 500, so I'm going to put 1 in here. 1 squared is 1, minus 500 is negative. So here it's going to be negative, which means it's decreasing. Something bigger than root 500? Well, how about 500? I know 500 is bigger than root 500. If I put 500 in there, I get some really big answer, like 250000, and if I subtract 500, it's definitely going to be positive. So it's going to be increasing here. Decrease, increase, this is a minimum. That's what we wanted. It's looking good. And finally, the question is, what were the dimensions? Well, we found the height could be either positive or negative 10 root 5. Wait a minute, the height can't be negative 10 root 5. So the height is definitely 10 root 5. And we got to figure out what the length is. Well, why don't we just plug it in right here? That'll give us the answer. We have 500 divided by 10 root 5. If you divide, you can cross off the 10 and the 0, you get 50 over root 5. You want to rationalize the denominator by multiplying top and bottom by root 5. And root 5, you're going to get 50 root 5 over 5. And 50 divided by 5 is 10. Hey, you get 10 root 5. So both the height and the length should be 10 root 5. Ugh, what a mess. But height and length both should be 10 root 5. And I guess for completeness sake, if we want the actual dimensions, we need to have a width as well. And it already told us the width is 10. It told us that right in the question itself. So width equals 10. So there's your three dimensions. 10 root 5 times 10. will optimize the question. Alright everyone, look forward to more of this, even harder ones, next time. Good luck!
This will be my monument.